This batch generates n-EDO scales. n-EDO stands for equal divisions of the octave, and it's a way of thinking about scales in which we create a scale by taking a note, its octave, and we divide the distance between those two frequencies in equal numbers of steps. For example, in Western music and popular music, we mostly use 12 n-EDO scales, right? We have a note, we have its octave, and we divide this distance by these 12 notes. But in this batch, it is possible to input different divisions of the octave. What I've just played was an octave divided by 8, so I can input 5 or 4 or 2 or 3 or 7, it doesn't matter. Using this patch and this logic of thinking, it's possible to create microtonal scales and notes, a whole new world of musical thinking where you can play around with new interval ratios, different intervals, different sonorities, different harmonies, and create interesting, cool music. So let's see how we can implement this idea using Max MSP. To consider a process like this, to take an octave and split it into equal steps and actually have it playable on my Max patch, I have to think of two things. So first of all, what kind of information do I need to send the patcher? And secondly, what has to happen here? What kind of process or formula or mathematical expression needs to happen here to convert the information I'm sending to this program to generate the result that I want? So to make this easier, much easier, I'm going to be using this formula here on the Zeno Harmonic Wiki, which is an open source for information about musical tuning, which gets very crazy. So we are going to keep it simple for now, and we are just going to look at n-EDOs or n-EDO, or the equal division of the octave, which is a tuning obtained by dividing the octave in a certain number of equal steps. This means that the interval between any two consecutive pitches is identical. And in fact, what the tuning system we mostly use, let's say in the real world, is 12 n-EDO, right? This is the Western musical scale that has been very prominent in the last few centuries. But the idea is that we have a note, we have its octave, which we perceive as the exact same note, and then we divide the distance between the note and the octave in a certain amount of equal steps. So all we have to do is to apply the formula to find the interval ratio for an n-EDO, right? And what does interval ratio mean? It means you take your, let's say, basis frequency and you multiply it by a certain interval ratio or a certain step size in order to figure out what the second or third or fourth or fifth or 16th or 25th or 5675th note of your scale is. For example, the step of 12 n-EDO, it says, is 2 to the power of 1 divided by 12, which might not make a lot of sense, but all we need is the following sentence. The formula for the kth step of an n-EDO is 2 to the power of k divided by n. Now, even if you don't know what this is supposed to mean or calculate, we can start by thinking of what kind of information do we need. And here I need two things, right? I need this k, which is the step I am at right now, and I need n, so the division of the octave. And turns out I already have the octave division here as an input, right? This is an integer number box, and I have made it for now that it will accept numbers between 1 and 8. So, you cannot put in something wacky like minus 55,524 or something like that, or you cannot go higher than 8. I mean, in theory you can, and I would completely encourage you to do that if you work on this patch. But to keep things simple, let's say we go up to 8. Now I need to create a process where I can find out an index number for each note, right? And if you're a programmer or if you have experience with text-based programming languages, you would be thinking of a for loop, but that doesn't really exist in Max. But what we can use instead is the closest analog to a for loop is Uzi. And Uzi will send many bang messages. That's in the name, right? I can give an argument to Uzi, let's say 5. And if I send a bang to the first inlet of Uzi, and if I print the results from the first outlet on my Max console, I'm going to get 5 bangs. So this is a very useful tool to trigger an event multiple times or control how many times a certain event is going to happen. But what's more interesting to me is the second and third outlets of Uzi. Now the second one will send a bang when it's done, banging, right? So what it means is after sending out these 5 bangs, it is going to send an additional bang here. So if we have a whole process and after these 5 steps are done, we need to trigger something else, we can use the second outlet. And the third outlet is the current index. That is exactly what we need, right? So as an argument, or on the second inlet of Uzi, I can select how many bangs are going to be sent, and those are going to be sent as the current index, right? In this case, this would be on which note I'm at in calculating the interval ratio of each note in my scale. So if I do it like this, for example, I can see 1, 2, 3, 4, 5. Which is great, but you will notice if we go back to this formula, we actually start counting from 0, right? This way when k, remember that is the step that we are at, is 0, which means the basis frequency, this whole function is going to give us 1, so we have to multiply our basis frequency with 1, which means it is that basis frequency. And when k is at n, which means the division of the octave, so if we are dividing the octave into 8 when we are at the 8th note, this formula is going to give us 2, which means we are multiplying our basis frequency with 2, which is going to give us the octave of that specific frequency. Right, so all of this means that we have to start counting from 0, and this Uzi does it by starting from 1, and I can simply use the minus operator, so -1, and then I can just subtract 1 from the result, and then I have 0, 1, 2, 3, 4. But this is Uzi 5, right? So I actually want to have 0, 1, 2, 3, 4, and then I would also like to hear the octave, so I would also need 5. So let's do it like this. I'm going to delete this argument, and I'm going to use this octave division integer number input to decide how many bangs Uzi is going to send. But first, I'm going to add 1 to this number, right? Because if I want to divide an octave to 8, I will need the index numbers 0, 1, 2, 3, 4, 5, 6, 7, and also 8, and that is in fact 9 numbers. So if I do it like this, and then I, let's say, send an 8 here, and then bang it, 0, 1, 2, 3, 4, 5, 6, 7, 8. Fantastic, this is exactly what I need. So now we have a way of getting all the different steps of my octave based on to which number I'm dividing my octave. Okay, and then I need the number n, right? Which is, well, the division of the octave, and I actually have it already. So I can already start with calculating k divided by n. And after that, all I need to do is to get 2 to the power of that number. So let's do it like this. I'm going to create a division operator, but as in the first initial argument, I'm going to give it 1 dot to make sure it's a floating point number so that the calculation is done with floating point numbers instead of integers. And then when I put in my octave division, I'm also going to load this value into the second inlet of my division object, which is going to set the right operand. It's not going to trigger anything, but then when I bang with my Uzi, I'm going to send all of these index numbers, and they're all going to go into this first inlet, and they're all going to be divided by my n, my octave division value. Let's see how this looks on the console. So first I'm setting the division, in this case it's 8, and if I bang it, there we go. So the first one is indeed 0, and then it goes on 0.1, 0.2, 0.375, 0.5, 0.625, 0.75, 0.875, and 1. So it goes from 0 to 1. If I had a division of, let's say, instead 5, so an octave is divided into 5, I would have, well, 6 numbers here. The first one would be 0, the final one would be 1. But now we are not done here yet, are we? Now I have to, let's see, I have to get 2 to the power of that number, so I'm going to be using the pow object, which computes input to the nth power. Now let's look at the inlets of this object, right? So the first one is raise x, so I know I need to raise x, and the second one is 2y, so then I know I'm going to raise 2 to the power of whatever value is this. So to send 2, I can simply create an object that is just 2. So this is an integer variable holding the number 2. And I can just send this number here. Now, the problem is the inputs, right? The inlets. The second one is a cold one. So on each step of my Uzi for loop construction here, I'm going to load up the second inlet, the cold inlet with the value. But each time I should also send 2 here in order to send an information to the first inlet, the hot inlet, which would trigger an output. And how I'm going to do this is I'm going to use a trigger object, or for short T, and then I can simply type in, let me think, B and F. Remember, in Max things go from right to left, so this means that first it's going to send out a floating point number that is coming in, right? And this result here is a floating point number that is being loaded up to the second inlet of POW, and then it's going to send a bang. B is short for bang to this to object right here. And this should technically work. Let's see if I can print this on my console once again, if I'm getting the right kind of answers. So octave division is 5, and I bang this, and there it is, 1, 1.14 something something, 1.31 something something, and so on and so on, and the final value is always 2. Okay, great. So now what I can do is I can take these values and I can pack them into a list. But I'm not going to use a pack object. I know I just said pack here, but I'm going to use ZL group instead. Remember, all ZL objects deal with lists. And what ZL group does, if you do not give it an argument, and if you keep sending values to its first inlet, it's going to collect it into a list. And this list is going to get bigger on each time until you send a bang to this very first inlet. At that point, it is going to take all those values it is containing and it's going to send them out as a single list. And luckily, we actually have a free bang at the end of this process, the second outlet of Uzi. Remember, when it is done sending all these bangs and index numbers, when it's done with all of those, it is going to send out a bang message. So I can simply take this. I can also plug it into the first inlet of ZL group. And let's see what happens. Let's say I want to divide my octave by 8, and boom, look at this. We have all the numbers we need in this list. And instead I can try, let's see, 2, divide an octave by 1. I'm not sure if that would work. No, it does work. Or 6, or 8. Doesn't matter. We are going to get this nice list with or interval ratios. Okay, so we have managed to calculate these values and put them into a list. Now, how to play them? So first of all, I also need my basis note or my basis frequency, right? So what I've done here is I've created a K slider, which sends out a MIDI note based on what I'm pressing here, and I'm using M to F, the object, to convert the MIDI value into a frequency. And I'm going to make this my base frequency, right? Let's say I start with this E here, which is in frequency terms is 329.6. And maybe it goes on even longer. Oh yes, a very specific number. That's frequencies for you. Okay, so I'm going to take this value and I'm going to save it somewhere, right? I want to trigger this number, send this number each time I am summoning a note, each time I'm triggering a note by using this keyboard trigger construction I've made here. I'm going to go into a bit more detail on that in a second. But for now, let's use the float object, which is going to store a decimal number. And I'm going to send this number to the first inlet of float, which is going to set an output, the value. Or I can, instead of doing that, I can send it to the second inlet. Okay, so now what is going to happen is each time I click on a note here, it gets converted into a frequency and it gets sent to the second inlet of float. This means that the value of this float object is set to that floating point number, but it is not sent out. Then what I want to do is each time I'm triggering a note, I'm going to get this float, I'm going to get a specific element of this list, and I'm going to multiply my floating point number with that interval ratio, which is going to give me the exact frequency I need to play that note in this very specific octave division. Now, to do this, I'm not going to use a musical keyboard, but I'm going to use my computer keyboard. So I've already set it out. Key is going to report keyboard presses, and then I'm taking the ASCII numbers, values of these keys, and I'm using cell to select specific keys here. So I'm on a keyword to keyboard, so I'm just taking, let's say, A, S, D, F, G, H, J, K, and L. All these 9 keys. So if we start counting from 0, 0, 1, 2, 3, 4, 5, 6, 7, 8 get triggered depending on what I am pressing. Right, to have a very quick demo, for example, I'm pressing A, I'm pressing S, D, S, F, G, H. Well, that would trigger 4, but that's not connected to this message box, of course. But this is a way to trigger bangs and other information from key presses. It's very useful if you are trying to create a patch that incorporates keyboard input in any way. And there's a reason I am triggering instead of bangs these specific number messages, because I have this list here, but I want to take this list, and each time I press a key, I want to look up a certain element of this list. And for this, I am of course going to use ZL lookup. And what lookup is going to do is it's going to either take the arguments that is provided, a list, or an input to the second inlet, which also should be a list, from which I will extract an element. Right, so I'm going to take the output of ZL group, I'm going to put it into the second inlet of ZL lookup. And then what I'm going to do is I'm just going to take all of these numbers and I'm going to plug them all into the first inlet of ZL lookup. And what's that going to do is it's going to call a specific element of that list, right? So let's say I'm using my basis frequency, I'm going to send a 0, the 0, so the first element of this list is always 1, so I'm always going to get 1, and then I can multiply that with my floating point number here containing the basis notes frequency that I have already provided. So let's make these a bit more useful by pressing Command Y, a bit more tidy looking. Okay, and let's see what happens now. So once again, I'm going to start this from scratch. Let's divide my octave into 8, and then I bang this UZ to trigger this calculation. And now I'm going to press keys on my keyboard. So the first note, 1, second note, third note, fourth note, fifth, sixth, seventh, and 8th. And then the next one will be the octave, which is 2. Great. So now I can provide a keyboard input, I can get my interval ratio. All I have to do is to also program in or patch a system where this does not only trigger this value, but also picks up this value of this floating point number and multiplies it with my interval ratio. And how I can do this is to use a trigger object. And again, in fact, it is the same structure, I would believe. So B and F. So first the floating point number coming from the ZL lookup, and then a bang. And then I'm going to already create my multiplication operator. Once again, as an argument, I'm going to give 1 dot so that the calculation is done using floating point numbers. And then when ZL lookup is sending the floating point number, first I'm loading up this floating point number in my second inlet of my multiplication operator, and then this bang is going to be sent to the first inlet of float. And the bang, as you can see here, is going to output the value that is already in this float, which is sent here, which triggers the calculation. I already have my second value, the right operand, and this should give me the exact frequency I need. So let's do this again. My octave division, I bang this, and then I put in my basis note. Let's make it A, so 440. And now when I'm playing this, as you can see, as I'm going up, it goes all the way up to 880 because octave is divided in 8. And to play this, I've just created a very rudimentary synth here. You can get way crazier with this if you want. This is incredibly basic, a cycle to turn these frequencies into audio, and an ADSR envelope with the max sustain 0, but the sustain off. So on each note, I can trigger a simple envelope. Right, and to do this, yet again, I'm going to use a trigger, so TBF, because I want to take this value, I want to load it to cycle, and then I want to bang this message box, which is going to send 1 to this ADSR object. If this confuses you or you're not very comfortable with these MSP objects and envelopes, etc., don't worry too much about it. This is just to sonify what we have been doing so far. You can create your own objects and constructions that take a frequency and turn it into audio as well. So let's hear this. Delicious. And we can try other divisions too, right? So I have to, let's say, put another number here, trigger this calculation, have a different bass note, let's say this low E, and then and if you want, you can go even higher than this. You can divide the octave to 12, and then it's a very complicated stuff for something you could have done already with this K slider, but you can divide an octave to 20, 50, 100, 6000. It doesn't matter. You can easily modify this patch to create even more color variations. And as I've said, you can also put in your own synth patch to get even more delicious musical output from this algorithm. But the point is, you explore this, you can explore it and have fun with it and have a great, wonderful musical time. Thank you for watching.